Uh, thank you all for inviting me. It's actually quite the honor. I suspect I'm going to be tuning in to several of these talks now that I hear them. I have been to the museum, so it's delightful to be here. So this topic, evolution of the Appalachians, right? It's really, really long, and people have been working on it for quite a long time. And I can only claim to have worked on a few small corners of the mountain chain. And I'll try to let you know what all the different pictures that I've included here are. I've combed through hundreds of photographs I've taken over the years, and some of them are better than others, but I'll try to comment on them. This first picture here is the northern terminus of the Appalachian Mountains in Canada. That is the very tip top of Newfoundland, and those are the Appalachian Mountains there. So let's give it a go. Um, I want to start first with just some really simple, basic terminology. I realize that there's a ton of jargon in all sciences, and geology is just full of it. I also realize that some of you know quite a bit about geology, so forgive me if I'm just talking about some things that you know quite a bit about. But I did want to start with a few baseline terms. And so to begin with, I've got this diagram of the differentiated Earth showing these different domains based on how we categorize different layers. But I find this diagram to be helpful in terms of just that 3D global structure, but my mind works a little easier on a 2D diagram. So I'm going to go there now. So we typically think of the Earth's interior based on two different kind of perspectives. We can divide it into these zones based on physical or mechanical properties. And we can also do it based on chemical properties. And so if you're like me, when I was in school, there was always the core mantle crust. And those are divisions based on composition or chemistry. The crust makes up a very small percent of Earth by mass, like 1%, and it's often rich in elements like silica and aluminum. So that's what I mean by a chemical differentiation. And the core is mostly iron, nickel, and sulfur. But if we divide the Earth into more mechanical layers, then we use some slightly different terms like lithosphere and asthenosphere, and those are based on those mechanical or physical properties. And so the lithosphere is one of those words I'll probably use a lot tonight. And so it's composed of both the crust and a portion of the upper mantle. And those units together, their behavior is more of a brittle, rigid solid. And then beneath that asthenosphere, it's that partially molten, flowable upper mantle material that can behave kind of plastically and can flow. I tend to think of it kind of like the old Stretch Armstrong, if anybody remembers it as a youth. And you're also probably familiar with the basics of things like plate tectonics. So I've got a little tiny plate tectonic a graphic in the upper right there. And so you know that the lithosphere can be divided into these distinct units, let's just say around 20, depending on whether you're a lumper or a splitter. But the buoyancy of things, the buoyancy of plates, it's a really simple concept, but it's really helpful in thinking about plate tectonics. For example, we'll talk a lot about plates, these lithospheric plates diving beneath or subducting beneath other plates. And one kind of first order question is, why does that subduction, that diving beneath even occur? And one good answer is the plate, one of those plates might be more dense or negative, or it might become negatively buoyant as the mantle part of a plate cools and becomes denser. Things get more dense as they cool, right? So this negative buoyancy is one of those kind of driving mechanisms. And the other thing to kind of keep in mind is just like an overall average density of the different lithosphere. And so like the average density of oceanic crust, we don't need to worry about numbers, but I don't know, it's around 3 grams per cubic centimeter. Water would be 1, so 3 times the density of that. And then the continental crust is a little less. It's something like, 2.7. And so there would be a tendency for oceanic crust to be at lower levels or to subduct beneath continental lithosphere. All right. A couple more things that are kind of on the knowledge that I want to come across with before we get going. And that's these three kinds of plate boundaries that I suspect many of you are familiar with. Divergent ones, I love these terms. I love jargon that just makes easy sense. Divergent, diverge, come apart when these plates go apart. Converge means they're going to come together, and these transforms means they're going to move sideways. And I'm a pictorial person, so I like to think of pictures of places that display these kinds of boundaries. So if we're standing in parts of Iceland and we could put our legs on one side of that crack and the other side of that crack, over time, our legs are slowly going to turn into a split as that divergent boundary progresses. A little harder to see, but the Cascades or the Cascade arc of volcanoes would be a classic example of a convergent boundary. The Andes would be another one. And transform, which I won't talk a whole lot about tonight, but the beautiful air photograph from a plane here shows the San Andreas Fault, which also happens to be a transform boundary in southern California. So those are, now we've got a few of these kind of basic terms behind us. I'd like to turn our attention to the mountain chain itself. And so here's a really neat map. I love this map put out by the U.S. Geological Survey in conjunction with the Canadian Geological Survey to make what they call a tapestry that shows geology colored by age of the rocks. And you can see the Appalachians there. I mean, you have to squint a little bit. But it's a lot of bluish colors there. And those are rocks that, I don't know, we like to use the word Paleozoic, zoic meaning life, and paleo meaning kind of before. And this is around, 540, 250 million years ago. So those are the blue colors. And then those orangey browns that you can see coming out, those are more ancient. And some of those can be 1 billion, 2 billion kind of years old. So while I think this map is really helpful for getting the idea of how the Appalachians fit into North America as a whole, we probably want to zoom into a bit more detail since we're focused only on the Appalachians tonight. And so to do this, I borrowed a little bit of Google Earth. I wish now that I placed the Appalachian Trail on there, but the Appalachians are about 2,000 miles long, and they go from the Canadian province of Newfoundland up in the upper right, where I've spent an awful lot of my time, and Labrador, all the way down to central Alabama in the United States. And sometimes we call it like the Appalachians, but really we're looking at something like 30 to 40 mountain ranges that reside within the Appalachians. And I don't know all 30 to 40, but they include things like the Chic-Choc, which are in Quebec, if you've ever hiked up there, or the Lone Range Mountains in Newfoundland, the Cape Breton Highlands in Nova Scotia, the White Mountains of New Hampshire and a little bit of Vermont, and a little bit of Maine, the Green Mountains, the Berkshires. Let's work our way south. The Poconos, the Catskills, the Cumberland, the Allegheny Plateau, the Blue Ridge. Let's get all the way down to the Smokies, and probably a whole more that I'm leaving out. So Appalachians kind of encompass all of those areas. Now, sometimes we like to turn that map that I just showed you on its side. So I'm just going to give you a second to kind of orient yourself with that Google Earth image that I just kind of clipped and rotated. And for tonight, I'm often going to give examples from places that I've personally worked. And so I'm going to focus on three kinds of places. And one will be Newfoundland, and the photo at the bottom will correspond to that. And then there'll be places like the Mid-Atlantic, maybe Maryland or South Mountain, which is that middle photograph. And then the very southern Appalachians of western North Carolina or the Piedmont of North Carolina. In this case, this is Grandfather Mountain, which are all kind of places that people who hike the Appalachian Trail are probably familiar with. Now, we can also overlay the geology, right, to get a sense of how complicated and variable the Appalachians are. And that map is already a simplification, but it's a mess. It's really hard to put anything into context or get the big picture from that photograph. So the next thing I'd like to do is simplify that as well. And this map was created by a good friend of mine named Jim Hibbard, and he tried to simplify the entire mountain belt into a group of sections of the crust so that they reflect something about their origins. And I think this is really, really helpful. And so they define these three lithotectonic divisions. And we'll use these words a lot. The first one will be something called the Laurentian realm. And the Laurentian realm, it's named after the mountain chain in Quebec. The next kind of realm would be something called the Iapetan realm. And probably a lot of you've heard of that word, Iapetan. The word itself means father of Atlas. And again, I think I love the roots because they help me remember things. And Atlas is who the Atlantic Ocean was named after. So Iapetus is kind of the father of Atlantic, so the predecessor of the Atlantic. And then the third realm that Hibbard and colleagues really like is called the Peri-Gondwanan, and that's like a mouthful. Peri just means around. And this Gondwana, I want you to, when you hear that word, I want you to think of ancient Africa and the continents that surrounded it at some point, and particularly India, because the word Gondwana is named after, it's named after an area and a people. So it's kind of two things in India. And so those words are used to characterize the erogen. And you can see that that some of these are really continuous and some are discontinuous on that map. So the Laurentian realm is composed of like native North American rocks. And it's remarkably uniform for the length of the erogen. Just really, that blue layer is really consistent. There might be a break there, but that's just because there's some ocean over top of it. And it records this multi-stage, complicated history of the Appalachians having this kind of passive margin, ancient seaways, and eventually the demise of both of those. And then this Iapetan realm, it really kind of focuses on this mainly oceanic and magmatic arc. I'll use that word arc a lot. And maybe I should just stop right now and explain how I'm using that. So we think of like magmatic or volcanic arcs because a lot of them end up having a view from space to be arcuate, kind of like the Aleutians archipelago or the Indonesian archipelago or Japan. So these volcanic islands that form this arc-like structure, in part because they're trying to accommodate geologic events that are on a globe that force that arc look. So volcanic arc, if you hear me say that word, just think of things like Japan or the Aleutians or something like that. And so that's a large part of that Iapetan realm. And then finally the Gondwana realm includes a whole bunch of different pieces of crust and lithosphere that are similar and not similar going from north to south. So in the south, you can see something called Carolinia, named because it's really common in North and South Carolina. And it goes all the way up in the middle of Virginia, but not absent, or at least not absent at the surface here in Maryland. And then there's this thing called Gandaria, which goes up to New England, Avalonia that goes partly through New England, but then stuck on the end of Newfoundland. And then this other one that's called Maguma that's stuck on the end of Nova Scotia there. But these all represent pieces of lithosphere that have some affinity, some tie to that ancient African Indian continent, supercontinent. All right. Now, so I said we're going to work on these three kind of areas. So before we get too far into the geology, I was kind of excited to hear you guys talking about the physiographic regions because I think they're really helpful to look at. So if we're Up in Canada, which I have their physiographic regions in the upper left up there, they look quite different from ours because a lot of that land has been scraped by those glaciers, and there's not a lot of what we call coastal plain up there. But I want to focus on Newfoundland in particular because that's the kind of the terminus of the Appalachians in North America. They might continue on over into Scotland and Norway, but that's not for us tonight. But Newfoundland is divided into these three kind of physiographic regions, kind of the Western, Central, and Eastern zone. And the Western zone has affinities of that Laurentian realm. And that's where those long range mountains are that I showed you at the very beginning, my opening slide that had my name on it. That's where those are from. And then there's that middle part that corresponds to the Iapetum realm, and then all the way on the east are all those different bays and headlands, and they look like little Chesapeake bays or little Delaware bays or Hudson bays, and that's because they are kind of submerged shoreline there. So those are bays or fjords up in that ways. And you can see the geologic map below there, which is still kind of complicated, but you can still see those three main zones picked out. On the left is a photograph from the western zone, and some of you may have been there. That's a gorgeous fjord in a UNESCO site called Grossmoor National Park, which is in that Laurentian realm. All right. If we move down to something more familiar to us, Maryland, I suspect everybody in this room has seen that upper right diagram many times, so I won't dwell too much on it. Except, of course, different from Newfoundland is we have that fall line, which generally follows Route 40 or Route 95 and separates those crustal Piedmont rocks from the coastal plain. And below there is a diagram showing the geology, and clearly there's some similarities there. The photograph on the left will be from the Piedmont of Harford County. I suspect many of you have been there, and that will be Rocks State Park. And behind me, or as I'm taking the photograph, behind me would be the King and Queen Seat for those who've hiked there. And on our journey, as we're going further south, I'm here with North Carolina now. And it's got these three basic zones in their physiographic region maps, which looks similar to Newfoundland, but also quite different from Newfoundland, right? And so we've got the kind of the Blue Ridge physiographic province on the far left, the Piedmont in the center, and the coastal plain on the right. And I put some words down there to try to explain some topographic changes as we go from the Piedmont to the Blue Ridge. Now that word Piedmont, kind of base of mountain. Then the Blue Ridge, which will be the mountainous area, obviously, to the left. But it goes through a transition between that Piedmont and the Blue Ridge where the land gets more topographic relief and more uplands. It gets more rugged, and we call that the Blue Ridge escarpment. And I have a nice photograph of that that's taken at the very end of North Carolina where it meets South Carolina at a place called Caesar's Head. And that terrain on the left-hand side of that photograph is what we call that escarpment, where those two kind of realms are meeting. Just like Maryland, just like Newfoundland, the geology's complicated, but it mimics these physiographic regions. But if I take this map and simplify it just a little bit, we can really glean a lot about the geologic history of the Appalachians in the southern Appalachians. So let's see. Here we can make out the Piedmont Blue Ridge and the coastal plains again. But I want to introduce a little new terminology. And I want to use the word basement because we've got a lot of basement in Maryland. So when I use that word basement, we're usually referring to old crystalline rocks, like igneous and metamorphic rocks, hard rocks, geologists sometimes like to call them. They're usually old crystalline igneous metamorphic rocks, and they're hard. And you can see I've got that as gray in kind of the upper left diagram there. And the cover would be sediments, beach sediments, gravel sediments, whatever sediments they are that are deposited onto these older basement rocks. So we got basement and cover. to make it just a little bit more of a twist in that upper left diagram where I've got basement. If you follow that to the right, you can see a little black area. And that would be that oceanic crust or oceanic lithosphere there. And so sediments that would be deposited on top of that, which are pink in this diagram, would be oceanic cover, right? So we've got continental cover and oceanic cover. All right. Now that we've covered that, we can go down and look at this diagram of North Carolina. And you can see I've got continental cover as part of the really far western Blue Ridge moving into Tennessee and the Smokies. And that's what's exposed at the surface. There are other rocks beneath that, but there's continental cover on the surface. And what should be underneath that is the basement. And we're lucky enough to see that basement in a large part of the northwestern part of North Carolina. So you can see I've got that word basement there. And then I've got a series of other kind of interesting labels. So that first pink layer, it'd be oceanic cover. So sediments that were later turned into rocks that may even later be deformed. So they go through sediments, sedimentary rocks, and they might even be deformed to other rock types. But that's oceanic cover. And then we come across this kind of green thing that says different oceanic cover. And we'll cover that, but there's two different oceans represented there with the cover that would be on top of them. And then moving further to the right, I got this thing called come from away. And you might recognize the come from away phrase that was popularized into a Broadway musical about the week of 9/11 when planes were forced to land in a place called Gander, Newfoundland, right? So that's my kind of tie all the way back to the north. And the saying come from away, if I were to put that into hillbilly language, and I am a hillbilly, if I were to put it into like Southern language, I might say, you aren't from around here, are you? And so those rocks, they're not from around here. They're from away. They're exotic terrains that don't have an affinity to North America. All right, so that's kind of the big picture of the physiographic provinces and some kind of details of really basic geology. And now we'll go into a little bit more details. And we are so lucky to be in the Appalachians. And I only know 0.0001% of the Appalachian story, but I feel really lucky to know even that tiny fraction. It's called a classic example of a complex mountain belt. That word orogenesis just means mountain building. So a complex mountain belt. And depending on where we were, it's at least 3, 4, possibly 5 separate orogenic events. I'm going to do a lot of lumping tonight because we're trying to characterize the whole thing into 4 separate mountain building events. And sometimes you hear this being referred to as a classic example of a Wilson cycle. When I hear Wilson, I either think of basketballs or the Castaway with Tom Hanks. But in this case, there was a guy named J. Tuzo Wilson who came up with this idea or a model that describes the opening and closure of ocean basins and subduction and eventual divergence of tectonic plates during the assembly and breakup of supercontinents. And the Appalachians are considered to be a classic example of this Wilson cycle. All right. All right, let's start. Let's start with the oldest rocks that we have, okay? There have been a bunch of different supercontinents. I don't know them all. The oldest is sometimes called but in our part of the realm, the oldest kind of supercontinent we have would be one called Rodinia. And it formed from a collision between 2 land masses that we're not always sure what they were. Certainly Laurentia, ancient North America, and maybe something that would look like South America or the Amazonian center. But these 2 masses came together and formed what we call the Grenvillian orogeny. So that's kind of the first of these mountain building events that I want to talk about. And the age of this event, it's going to vary a bit, but we just kind of throw out this 1.1 giga or billion years ago. So this giant supercontinent over a billion years old. And it lasted around for quite some time and slowly started eroded away until by like 600 million years, which is a long, that's 600 million years later. It's a long time. Much of that had eroded away. So I say that we've got this Greenvillian orogeny. Are there any Greenvillian rocks around? Do we have evidence of these things in the Appalachian orogeny? And I think that's always the question that we want to ask. If we make some statement, do we have any kind of evidence for it at all? And so we do. We do have evidence for these Greenvillian rocks or this Greenvillian event. So the map in the upper left is just black and gray, but those black areas indicates where there are large exposures of rocks that are 1.1, 1.2 billion years old and representative of that Greenvillian event. All right. And over on that picture on the right, we're just showing kind of the configuration of this supercontinent that was around a billion years ago. And in the kind of the lower left there is just a reminder of the compressional tectonic event that created this Greenvillian orogeny. All right. So I'm saying we've got evidence. There's some black dots there showing we've got rocks for it. Let's see what some of them look like. All right. So the Appalachian Mountains contain lots of these small, well, sometimes large exposures of these Greenvillian orogenic mountain building rocks. And so the largest of these that are in what we normally call the Appalachians are the long range mountains. And those were in Newfoundland. And so I'm showing two pictures of those at the top of this slide. One, you can see the rocks themselves in yet another fjord, and then kind of a close-up of these billion-year-old rocks. You can see the snow in the background of Western Newfoundland. Another big outcropping of these rocks is the Adirondacks, and the Adirondacks are, I mean, they're gorgeous. I've only been to a fraction of them. I even remember when the Olympics were held in. And so here on the left is a picture of one of their mountains called Gore Mountain. And that, again, is a 1.1 plus or minus billion-year-old rock. And on the right is a close-up, and that's a quarter kind of for reference there, of these giant garnets. There's actually a garnet mine. These beautiful, beautiful red garnets. Some of the garnets there are meter size. They're yardstick size. I've only seen pictures of those. I've never seen them myself, but these garnets here are bigger than your fist. And so they're, again, examples of this Greenvillian orogeny, this mountain building event a billion years ago that was responsible for a supercontinent that is long gone called Rodinia. Well, let's keep going, right? Moving our way down through the Appalachians. The picture in the upper left is what we call the Baltimore gneiss. It's a really easily seen, really resistant rock. You can see it a lot in the area. I'm used to seeing it a lot in and around Towson. And again, it's a 1.1 billion year old basement rock. And that particular one in the upper left is from Carroll County. And in the upper right is one of my classes, and we're actually on the campus of Towson University near the football stadium, just down near a parking lot. And there is a just gorgeous example of the Baltimore gneiss there, a Greenvillian aged gneiss with lots of folds. You can slightly see some of those folds in the upper left, and if these folks were out of the way, but I don't want to move them out of the way because I like them, you would have seen a lot more of these folds. And there's some other examples. So again, I'm trying to do this three-phase thing. In the lower part of that diagram, we've got some examples from the Appalachians near the North Carolina-Tennessee border. You might know the Roan Mountains or the Roan Highlands. And the rock there is called the Cranberry Gneiss. And so that's a picture of it in both the left and right-hand side. Since a bunch of you are hikers, I wish I would have got some pictures of these areas, but other examples you might know of, as you're driving along Skyline Drive, a lot of those rocks are these basement billion-year-old rocks. Old Rag Mountain, Mount Rogers, some other kind of really popular hiking places. All right. Well, all good things must come to an end. And in this diagram, 650 million years ago or so, in a tectonic reconstruction, kind of shows Laurentia in that kind of central position. It doesn't look anything like what we're used to seeing. It doesn't look anything like it at all in this particular case. But we're starting to see the breakup of Rodinia here, right? And so it started rifting apart, around 600 million years ago. And that's my top diagram there. And you can see those little curved lines are fault lines. And they're showing these little down-dropped basins that you can think of. And those basins are just great places for mountains to erode into. And as that ancient continent started to pull apart, it formed a new ocean, a pre-Atlantic ocean, right? And that's what that lower diagram is there. And so on the left part of that diagram, we've got kind of ancient North America, ancient Laurentia. Then we've got a piece of oceanic lithosphere, oceanic crust there, that I put that iapetus word below that to signify that that's something that's the iapetus realm. We sometimes call that the iapetus ocean. I want to say the iapetus ocean was really complex. It wasn't just one nice, pretty ocean. It was a complicated ocean. Kind of think of Southwest Indonesia with all those different little islands and little small kind of seas and ocean dividers. But for this purpose of this diagram, we have the iapetus ocean. And then off to the east there's a couple of things. There's some kind of volcanic arc. Again, I'd like you to think of that as a Japan or something like that. And you can see some of that oceanic lithosphere being subducted, going down beneath that landmass, eventually melting, creating some of that volcanic activity that we see in that diagram. Okay, great. What else do I want to draw attention to? Yeah, over on the left-hand side, on the bottom of that diagram, you can see those little maroonish brown dropped down basins, fault-bounded basins. And on top of that are some kind of yellowish shape with some little dots in it. And those are to indicate sediments being deposited on this rifted apart margin of ancient North America. Okay. So let's look at some more rocks now. So this Laurentia started to drift away in that, 600-700 million years ago. And rocks are being pulled apart. There's these tensional forces. And so you can imagine a series of cracks and rifts that form throughout that whole Rodinia landmass. Also, there was, just as an aside, Earth experienced one of the most extreme periods of glaciation in its history during this time frame, and ice sheets went all the way down to the tropics. So kind of interesting. And around 550, 560 million years ago, these continents that made up Rodinia, they split apart totally, right? Totally at that major rift. That I just want to go back really quick and say that I'm focusing on this kind of bottom part of the diagram now. All right. And the rift that happened caused this breakup of Rodinia. It got flooded as sea levels kind of rise, and it transformed that continental margin to kind of an oceanic crust, basaltic crust, if anybody likes the rock names. And that rift eventually became that iapetus ocean, and it's marked by ancient sandstones that formed along see where the word Paleozoic is in the word Paleozoic passive margin. Those sediments below there are the eroded remnants of the former Grenvillian Mountains. Okay. So are there evidence for those rocks? And so the answer is going to be yes. So my favorite example that I don't have a picture of, I've never taken a picture of it, but if you've been to Pilot Mountain in North Carolina, that's like an ancient sandstone that represents those rocks. Some other rocks that aren't quite as dramatic, but still represent rifting, erosion, and deposition of sediments from those old Grenvillian Mountains that are long gone, but the remains of them are detected in these sediments. They are places like the top two photographs, which are from Newfoundland, which have just dramatic exposures of sediments representing the breakdown of those Grenvillian Mountains. And we also locally are lucky to have some sediments, some rocks that are derived from those sediments as well. So the lower left picture is what we would call the setter's quartzite. I wish I had a better picture. It's a common building stone in the area. It often has the mineral tourmaline, a black, pretty mineral in it. And you can see it. Oh, I know. The best place to actually kind of see it and touch it would be the Big Screen Store in Baltimore. That slope at the Big Screen Store is made of this rock. And again, it represents sediments that filled in those. I'm going to go back to it because I want to focus on that diagram. Go back. Sediments that filled in this rift basin below that word Paleozoic in the bottom diagram. Sediments that filled that in eventually became sedimentary rocks, and through later tectonic events, they got maybe metamorphosed and changed. But these rocks, that setter's quartzite represents that. The next rock on the right is what we sometimes call the Loch Raven schist, and it represents sediments that were deposited a little further away from the ancient Laurentian margin. And then all the way on the right is a rock that many of you will know, but you might not recognize that photograph. That's actually the Cockeysville marble that a lot of you are probably used to seeing behind the Hunt Valley Mall, which is a beautiful exposure. But I like this one because you can see all the folds in that marble. Now, it's a marble now, but a long time ago, it used to be a limestone that was deposited off that ancient Laurentian margin. Okay. Oh, wait, I did include a picture of Pilot Mountain, but it's not my photograph. It belongs to my friend Jim Hibbard. And so these are sediments from North Carolina that represent that same rifting event. So on the left is a beautiful hiking place. I suspect a lot of you've been there. It's Grandfather Mountain. And those rocks represent rifting of the ancient Laurentian. And then Pilot Mountain, and then a close-up of some of the rocks with all these big, giant, gravelly, small boulder-looking rocks on Grandfather Mountain. And those would represent sediments that were maybe deposited in a fast stream coming off those Grenvillian Mountains. All right. Okay, I've really pushed a lot with those rifted sediments. Let's move on to something else. So I mentioned that as that ancient Rodinia is being pulled apart, there's going to be all these cracks and rifts that show up. And many of these did become basins that get filled up with sediment that became sedimentary rocks and that I just showed you examples of. And a lot of these ancient rift basins can be seen in rocks around Catoctin Mountain Park as well, or South Mountain. But I'd like you now to imagine the Rodinia being pulled apart. Instead of just some continent with this funny name, let's picture a cold Snickers bar that's been in the refrigerator, or a Milky Way bar that's been in the refrigerator. And let's slowly pull that thing apart. And it's going to get thinner and thinner and thinner. And if that represents lithosphere, as it gets really thin, that's going to allow that warmer, hotter plastic asthenosphere to rise up and bring hot magmas up through those thin cracks those thin cracks that occur in the Snickers bar, or what we're really talking about, of course, is the lithosphere. And so magmas and lavas erupted through those cracks. And so do we have evidence of that? Well, yes, we do. And we call those the catoctin formation. And sometimes there were really thick piles of lava that cooled. And if you've ever been out west, you'll see a lot of times these thick piles of lava, they'll cool and they make these characteristic honeycomb hexagonal patterns that we call columnar basalts. And so that photo in the upper left there shows a picture of some of these lavas that would have been on the surface millions and millions of years ago that would have cooled into these hexagonal patterns. And that's my class from last year. And so we are looking at ancient lavas associated with that rifting of Rodinia. And in the lower right is kind of a close-up of what those rocks might look like. And the diagram in the upper right, I just wanted to point out, because where we see some of these rocks today were probably not where they were created. So these lavas and magmas that erupted and make what we call the catoctin formation today were at one point 100 miles west of here, and then they just got pushed westward through later tectonic events. Remember, we've only got through one orogenic event so far. We've got a few more to get through. So they've been moved, I don't know, 70, 100 kilometers west and became shortened, and we've lost a lot of them through erosion. But we're lucky to still see them. All right, time for our second kind of major orogenic event, and it's called the tectonic orogeny. And it's been contentious. So I'm going to lay out a fairly simple story with it, but it really is still a bone of contention amongst a lot of different folks. The overall main details we get, but the more nitty-gritty is still under a lot of debate. So typically, we think of this event as having like multiple phases, not just one simple one. So there might be one of these different accretion events, different events where we are accreting or adding different land masses to ancient North America, building up, kind of like you can think of them a little bit like an accordion, as we maybe have one volcanic arc dock or get docked onto the ancient North America, and then maybe another one gets docked and another one gets docked. So again, when I talk about these arcs, I want you to think of Japan or the Aleutians or something like that. Do we have evidence for some of these arcs, like I'm talking about in the upper right corner of that diagram at the top? There's that little volcano, that magmatic arc. Do we have evidence that that arc existed, right? So I want to go through that, and we absolutely do. So my first photograph on the left and right of the top are from something called the Cape Ray Igneous Complex and the Twillingate granite. Actually, all four of those are from that. The top's from a place called Cape Ray, and the bottom is from a place called Twillingate. That's my class from about 4 years ago. And we are standing on top of rocks that were once the roots, the basis of one of these magmatic volcanic arcs that are lucky enough to be exposed. And where are they? They're in central Newfoundland. All right. So got a more complicated diagram here. So most ancient rocks in the core Appalachians or the Blue Ridge are related to these kind of old 540 or older tectonic events like the Grenvillian orogeny that I've been talking about. But a lot of the Piedmont rocks, whether you're in North Carolina around Raleigh or here in Baltimore or up in New Hampshire or all the way up in Nova Scotia and Newfoundland, a lot of those rocks actually formed somewhere far away from North America and just were attached as this patchwork of islands and fragments of land that we often call exotic crust. In the same way that we saw exotic plant species, not from the place that we're talking about, in this case, ancient North America. And so many of these Piedmont rocks, they've been metamorphosed a bunch of different times, and it's really difficult to tell their exact origin and the ultimate age of formation. But nevertheless, we're able to at least separate them into these Iapetus realm rocks and these Paragondwana realm rocks, which is what we're moving into now. All right. Now, in the lower part of this diagram, I've got two things going on here. I've got some continental crust, some oceanic crust on the left-hand side, and I've got that word ophiolite there. So if we're eventually going to destroy this Iapetus ocean, this ancient ocean, we might get lucky to preserve pieces of that ancient oceanic crust and upper mantle. Some of them might get broken off. They might get incorporated into other rocks and kind of abducted onto the continental land masses. And so these resulting rock sequences of oceanic lithosphere, so crust and upper mantle, are really helpful for studying timing of events and for studying the oceanic lithosphere in general. And we call them ophiolites. Again, I like roots words of things, and that means green serpent in Greek. And so the rocks tend to be kind of green. I don't know how complicated we want to get into them, but there's a sequence of them that's in that rectangular box on the lower right that tends to have like the perfect sequence of rocks that we would see in an ophiolite, with, you know, a bunch of sediments deposited on basically the bottom of the ocean floor, maybe something we call pillow lavas, where lavas have erupted onto the ocean floor and been preserved, maybe some other older rocks that have intruded through cracks beneath that, and then some other rocks, including pieces of the mantle at the very bottom. And so we call this an ophiolitic sequence. And this would, if we see these, then they could be representative of a piece of that Iapetus lithosphere, all right, or some other oceanic lithosphere if we were in other parts of the world. So my next question, do we have evidence for these rocks being incorporated into the Appalachians? You're probably getting tired of me saying that because you know I'm going to say yes. And it's important that we always have a yes to these questions. So we do have them. So before this tectonic mountain building event that I've been talking about, it's important to realize that North America was missing like most of what we call New England. It just wasn't present yet, hadn't been attached yet. And so New England's slowly been pieced together, as well as places like eastern North Carolina, slowly been pieced together by strips of land that have been added to this proto North American continent. And remember, we call these exotic terrains, come from a ways. All right. But eventually, of course, they do get added and become most of Vermont, New Hampshire, central Massachusetts, Connecticut, Maine, Nova Scotia, Newfoundland, etc. But where they become attached, would be place where they were kind of stitched together, sutured together, and we can look for these suture zones, these places where these microcontinents or land masses have been glued together. Places where these come from a ways were docked onto ancient North America. And if we're looking for places where this ancient oceanic place got kind of squeezed away as it was maybe subducted beneath another landmass, we'd be looking for these ancient, unusual ophiolitic rocks. And I think one of the best examples in all of the Appalachians are something called the tablelands. And that's all of these pictures on this slides here. And what you're looking at in the tablelands, which are in Newfoundland, western Newfoundland, they are pieces of the Earth's mantle. They form these desolate but colorful landscapes, right? You can see all that orange, right? Yellow, orange, red. Sometimes they're even green and blue rocks in that kind of lower central one. And they're mostly, in this case, a rock called peridotite. If anybody has the August birthstone, you'll recognize peridot as the name, which is a green mineral. Geologists like to use the word olivine there. But when that mineral gets transformed during tectonic processes, it forms another rock that I'm willing to bet everybody in the room is familiar with, called serpentinite. Serpentinite and some other words that we might use as well. So the tablelands are composed of these rocks composed of ancient oceanic crust and mantle, and they have unusual properties, unusual chemistries. They're really high in nickel, they're high in magnesium, they're high in chromium, iron, cobalt, and have some unusual minerals. And because of these unusual minerals, these unusual chemistries, they have unusual soils, and they're often home to really specialized endemic plants like that serpentine aster in the lower right-hand corner. So all of those are from Newfoundland, and frankly, it looks like Mars. It just looks like a world that is not what normal people deal with. Speaking of these specialized plants and specialized rocks, here's the one that I know everybody in this room is familiar with. Here is in the lower right-hand corner, the serpentine aster from Soldier's Delight. Actually, that's from Nottingham in Pennsylvania, that photograph. The upper left-hand photograph is Soldier's Delight. The lower left is going to be Lake Roland off of Falls Road, that I'm sure some of you are familiar with. And in the upper right is a hand sample that I've gathered just to show you how green that serpentinite can be at times. But bottom line for us on Evolution of the Appalachians, all of these rocks represent oceanic mantle from a piece of oceanic lithosphere that is long, long gone. So we met northern Appalachians, central Appalachians. Well, let's just go to the south. So here we are back in North Carolina, and it should look really familiar to those of you that are playing with Soldier's Delight, except it's more mountainous in the background, right? And this is a place called Bucks Creek, and it's in the Blue Ridge, kind of near Asheville, North Carolina. And again, it's a piece of this ophiolite, this ancient oceanic crust and mantle, and it's beautiful serpentinite rock in the lower left. And those flowers there, I'm not sure I can remember them all. Bluettes, azure bluettes, serpentine ragwort, and there's some paintbrush there, Indian paintbrush for people that really like that. There'll be little red spiky things that are a little bit hard to see. Beautiful place if folks like plants. It's a gorgeous place to go in the springtime. All right. Now, we've got these large chunks of rock that represent these come from away areas, but the type mountains would have been these tectonic mountains, and they would have been a band of mountains from, again, Vermont, New Hampshire, Western Maine, all the way down, forming the Eastern Blue Ridge. And as these rocks are being formed, as the compressional convergent tectonics are happening, I want to draw your attention to that diagram on the upper left. So you've got the tectonic mountains that are eroded mostly away now, but behind them, there's forming another kind of basin and an inland sea, and rocks are being deposited there. So this downwarping created what we call the Appalachian Basin. And there's sediments being deposited there that are coming off of those ancient tectonic mountains and forming deltas. The Queenston Delta is a really famous one that fans out towards the Great Lakes, and it forms a wedge of sediments kind of away from the ancient tectonic or kind of Eastern Blue Ridge kind of area, and again go all the way up toward Niagara. And that photograph on the lower left is from the rocks that represent this inland sea delta, and that's near Niagara. So those are those kind of reddish maroonish colors. Now, eventually, these tectonic mountains eroded almost all away until we only see kind of the core of them. And so we still have evidence of the core of these mountains, and that's that picture in the upper right, and those are the Berkshires. And the Berkshires in New York are the roots of that kind of ancient tectonic kind of mountain range. All right, I know I need to hurry up a little bit, but the tectonic is the really important kind of one, so I'm kind of focusing on it quite a bit. So after the tectonic, most of eastern North America was really quiet, although Newfoundland and Nova Scotia had a separate little tectonic event at that time. But this proto-Atlantic eventually kind of closed up. Prior to this, by the way, just as an aside, prior to this like 400 million year old time frame, there really weren't any land plants, right? So these were kind of barren looking continents. But around this time, land plants are starting to take over. And eventually, as we move kind of getting closer and closer to time, we see just what I want you to see in this diagram is just how complicated these little oceans are between ancient North America and that Gondwana. It's just really a complicated series of oceans and islands in there. And so that brings us back to the big picture. So now we're ready for our third big tectonic event, right? My next orogeny. This one we'll call the Akkadian orogeny. So let's put the backdrop of that one. So this peri-Gondwana realm that I've talked about is composed of a bunch of these come from arrays. I'm repeating myself. That are the Carolinian terrain, the Avalonian terrain, the Maguma terrain, all these different terrains that we don't see here in Maryland, but they're north and south of us on both ends. And so in my top diagram, you can see how that tectonic mountain building is on the left. And then there's a new ocean there because we closed another ocean. So here's another ocean. We can call it the Rake Ocean. Over to the right of it, another piece of exotic crust, yet another come from away that we'll connect and we'll hook up with it at some point. So I wanted to show some pictures of what some of these come from away rocks look like in the Avalonian terrain, which is mostly in the Canadian area, but we can see some in Cape Cod. And all of those pictures in the lower diagram are from the Canadian Appalachians, and that's the Atlantic Ocean you're looking at in the first one on the left and the second one in the middle. And so we're right on the edge of the ocean there, and all of those rocks, you can see why they don't have any coastal plain. It's just pure rock up there. Those are exotic pieces of material that have been accreted or added to ancient North America. And just for fun, on the right-hand side, where there's a little penny for scale, you can see what looks like a little fossil there. And those are the first multicellular life forms that we've kind of recorded in a place called Mistaken Point, again, in the Canadian Appalachians. All right, let's notice what I did in this diagram from the last one. I'm taking that piece of exotic crust on the right, upper right, and I'm going to dock it or accrete it or smash it into the diagram on the left. And it's just getting more and more complicated on the left. And here's our Akkadian orogeny, the third of the four big mountain belting events. I've got kind of a diagram in the lower right of what the continents kind of look like at that time. And so do we have some rocks that represent this? Yes. And so I want to show some of those. On the right-hand side are two just spectacular examples from the top one's called the Burgess granite. The name's not important, but it's in Canada, it's in Newfoundland, and it represents that Akkadian arc that we accreted. And the below is from, I just love the name of this one. It's called the Catskill terrain. Just like it's from a town called Catskill, and that's in North Carolina. Though there are some rare mafic and ultramafic rocks associated with this orogeny, they're hard to find. They're not very well preserved like the other ones that we associated with, like Soldiers of Light. They're just hard to find, and not as well preserved. There are some in that Catskill terrain and in Newfoundland, but they're small. They're not as widely distributed. But this Acadian event is really important for New England and the New England Appalachians, and it really structures a lot of what we see there. It was a very intense, deeply seated, very aggressive, high temperature deformation event, and forms a lot of what we see in Vermont, New Hampshire, Maine. And on the right-hand side are some smaller garnets. Those are not Gore Mountain garnets. Those are smaller garnets from Vermont that were created from the heat generated from this particular orogeny. Just like the tectonic orogeny, compression makes another kind of inland sea warp down the crust. So just replace the word tectonic in this diagram with Acadian Mountains, same diagram. There's an inland sea off to the left, and sediments are going to be deposited as these Acadian rocks are slowly worn down. And what do they form? Well, they form the Catskill Delta. So a lot of the Catskills are formed from sediments that eventually became rocks that were formed from the breakdown of these old mountains associated with the Acadian orogeny. And that's what that picture in the upper left is. All right. Just another kind of picture of where the continents were, around this time, around 300 million years ago. And we're going to get really, really towards the end now. So we're going for the last of the four major mountain building events, the Alleghanian orogeny. And so my diagram in the top, you can see I've got roots of the ancient Grenvillian rocks on the kind of the far left. I've got these tectonic orogeny rocks that are kind of orange and red. I got these Acadian orogeny rocks that are kind of brown. There's a little tiny ocean there that's being subducted away. And here comes kind of ancient Africa that's also going to dock with North America. Around 270 million years ago, depending on where you were in the Appalachians, and that's what we call the Alleghanian orogeny. And it creates a lot of what we see in the central and southern Appalachians, a lot of what we visually see as the topography. This huge, like, folded rocks and faults where rocks have been thrust westward into creating these mountain range, and is responsible for that supercontinent Pangaea. So here I've kind of squished it together. There's all of the rocks into the Alleghanian orogeny. That's when Pangaea is kind of being put together. That's what's represented in the lower left. And just for fun, because maybe I didn't explain much about my background, but I'm going to try to get this straight. The son of a son of a son of a son of a son of coal miners from West Virginia. And so that picture in the lower right is from our newest national park, which is in West Virginia, called the New River National Park. And so that's the New River that's going around those little headlands right there. And at the time that this Alleghanian orogeny was happening, we had a really tropical climate. There was these enormous coastal swamps all along the margins of retreating seas, and vegetation fell into these swamps. It became stagnant, these oxygen-poor waters that slowly decompose, and they form these huge deposits of peat. And then sediments fall on top of those, sediments from the eroding mountains, of course, and eventually compressed that peat and made it the largest coal beds, or one of the largest coal beds in the world, which is why I focused on West Virginia there. And the little tiny blurry photograph in the upper right there's a little contention here. It's either the last or second to last company store left from the coal mining camps. And I'm lucky enough that my father actually worked at that particular mine, and I went to that company store daily when I was a teenager, getting a sandwich that mysteriously I didn't have to pay for because it was at the company store, so it came out of my father's paycheck. But anyway, so there we are with the coal. And this mountain building event, like I said, is responsible for kind of the basic Appalachian structure that we see. And kind of like the Acadian orogeny before it, the Appalachian actually kind of began in the north and worked its way south, kind of closing that ocean like a zipper. All right. And a lot of piece of crustal components were moved westward, as much as, and so the crust to the west was shortened by almost 120 miles in most places in the central and southern Appalachian Mountains. And although they were kind of formed, 250 million years ago, a lot of that components are still with us today. You hear it talked about all the time. Once perhaps they were as tall as the Himalayas, but the same thing can be said of those Grenvillian Mountains. They would have been really, really tall as well. But now they've been beaten down, rounded, weathered, aged. And so the photo on the left is Newfoundland again, and it's showing a fault, a trace of a fault. So that valley where there's a little tiny stream, but that's a fault called the Lone Range Fault. And it actually separates kind of Laurentian rocks on the left to these Perry-Gondwanan rocks on the right, which is kind of cool. In the middle, I bet everybody has seen it. If you hadn't, you need to get out there. That's Sideling Hill. And those folds are from the Alleghanian orogeny. And the far right is that kind of folding and thrust fault terrain created in the Blue Ridge and the Smokies, in this case, of North Carolina. And so there's kind of where the continents looked as we're getting closer and closer and closer to the modern day. Eventually, of course, Pangaea split apart. We're getting to the story that just about everybody knows. There are all these rift basins. There's Mesozoic rift basins, we call them, just like we saw before. These faults, these blocks of crust that are falling down and eventually get filled with sediment. And we should always look for evidence of these things. And we've got a lot. There would have been a series of these rift basins. And I actually like to think of East Africa, the East African rift, when I think of this as an analogy where, if you kind of look at that from space, there's a western component, an eastern component, the Red Sea's kind of in between. That's how I imagine the early Atlantic to have looked like on either side of that divergent boundary. And so sediments were deposited into these basins. And they often have a kind of a red or maroon look to them, and they're really kind of gravelly and conglomerately because they were just deposited right at the base of the mountains. And so these are all examples from Newfoundland on the upper left. See, I don't want to get these wrong. Culpeper Basin in the upper right, like Culpeper, Virginia, that goes all the way up to kind of Seneca, Maryland, and at the foot of the Catoctin Mountain. And then the one in the center down there is from North Carolina again, and it's what's called the Durham Basin, the Triassic basins, people call them, which is near Durham, North Carolina. We're slowly breaking up. Here's my diagram. You can see the little Atlantic forming. North America is going back to its position that we're getting kind of used to. And I want to just kind of wrap up with two kind of review diagrams that I have nothing to do with. I didn't create either one of them. This first one's from the National Park Service, and I just think it's wonderful, and I think about it all the time. It just shows a cross-section from the kind of central and southern Appalachians going from east to west, coastal plain, Piedmont, Blue Ridge, Valley, and Ridge. And it places on top of it kind of some of the parks that are in these different areas. So if you're at Great Falls, you're in kind of a Piedmont area. And so there's lots of those come from away terrains there. But if you're all the way out where my family lives in the New River Gorge area, you're way out in that fold and thrust belt. And in fact, to be fair, West Virginia, we think of as the mountain state, right? But if you look at the rocks in almost all of that state, they're flat as pancakes. They're not tilted very much. They're not folded very much. They're flat as pancakes. And we actually call that the Allegheny or Cumberland Plateau because they're just flat rocks. And all those mountains in West Virginia are really just created by rivers down cutting through those rocks. So again, look at those rocks in West Virginia when you're out there. Not like Harper's Ferry. I'm talking out in the more western part of West Virginia. You'll see that the rocks are flat, and all of that relief comes from streams and rivers down cutting through rocks over time. So great photograph that I think really puts things into perspective. And finally, this is what I've talked about from top to bottom. At some point, I'm sure I'll hand over these slides that folks can look at in the future. But summarizing our Greenvillian orogeny, the rifting of that, the creating of an ancient ocean, slowly accreting one exotic terrain after another as we go through these different orogenies, finally culminating in the Alleghenian orogeny, where everything gets really pushed to the west. And just a teaser for the future, just a teaser. I don't want to go too far in the future, but this is just 50 million years. The Atlantic Ocean should keep getting bigger and bigger, and the Pacific Ocean should keep getting smaller and smaller, and we should have another kind of supercontinent on the other side of the graph. I won't be around for that. I don't even know what they'll name it. I kind of like Amasia, just kind of like that, but we'll see what those future geologists come up with. So I'm sorry for going so fast. I do want to thank thousands and thousands of geologists and papers that I've read, but specifically 4 people that have been really fundamental to my understanding. And I will mention their names. Kees van Staal, who's a Canadian geologist, Jim Hibbard, who's a structural geologist from North Carolina, Michael Brown's University of Maryland, and Skip Stoddard's at North Carolina State. And they've just been terrific models. And there we're looking at the Southern Appalachians one more time. So, all right, I will stop now.
Woo! Thank you so much. You left a beautiful talk on a beautiful image. Let me get a spotlight on you, Jerry.
Okay, I'm trying to quit some sharing here and things.
Okay, and now we'll open it up for some questions. We do, if you want to put a question in the group in the chat, you can do that. This was amazing. I feel like I've taken a whole geology class in an hour. It's wonderful.
Well, the fun thing about such a geology class is, if you take one from a main geologist, you'll get a version that's slanted a little bit more to New England, right? Or if you take it from Georgia, somebody's going to slant it more to the northern. So I tried to cut everybody a little bit with that northern, central, southern Appalachians to kind of do everybody some due diligence. But
yeah, it's just so fascinating. I just had a question real quick. The garnets that are found in Maryland, are those Greenvillians, or they come from later ones?
Oh, so that's a really, really good question. And there are, of course, garnets in lots of different places in Maryland. So that'll make the answer, it depends. So if the garnets that you look for, and the closest place that most people look for them are up, the famous places like up behind Hunt Valley Mall, right? People love to look for garnets near the parking lot up at Hunt Valley Mall. Those garnets are not Greenvillian age. Those sediments are from Greenvillian rocks. Those sediments were turned into sedimentary rock, then turned into metamorphic rocks, and those garnets grew. To be honest, we used to think they grew solely during this tectonic event, but a colleague of mine who did a postdoc here at Johns Hopkins 2 years ago named Freya George, who would be also a great person to invite sometime for a detailed.
Jerry, she did a talk for us. She did a talk for us.
Oh, okay,
Yeah,
great. So she looked at some of those garnets in really good detail. And so those, it seems like a lot of them grew during that older event, and some of them seem to have grown during a slightly younger event that we don't understand very well yet. But if you go out in Western Maryland, the Blue Ridge, like Skyline Drive, and look for garnets, and you'll see them. They might not be as pretty, but they'll be there. And those will be billion-year-old garnets out there.
All right.
Or Grenvillian age garnets.
Let's see. Steve asked, is there evidence for major cooling and heating events produced by CO2 pulled, released, respectively, from the atmosphere during weathering and erosion of the Appalachians? I guess CO2.
Yeah, there's a lot. And Steve, that's a superb question. And I'm going to first just say I'm not the best one to answer that because I don't look at atmospheric concentrations very much. But yes, all right. So like the easiest example is when those coal swamps were, these peat swamps, and coal was being formed in the Appalachians, there was a tremendous drawdown of CO2 in the atmosphere, really, really low. And coincidentally, at that time, more evolved land plants and forests were encroaching upon the continents, elevating oxygen at that time. And so we saw kind of this cool, really drawdown of CO2, but a really pump up of oxygen as photosynthesis starts to kind of take hold on land. I wish I knew more, Steve, but I other than to answer yes, I don't know the details of them.
Will asked, where do you think the biggest unknowns are in Maryland's geologic interpretation?
Yeah, I tell you, so I think that Maryland geology is being given short shrift over the years. It's not been studied near as much. I think that we actually have some extremely complex, wonderful, beautiful rocks to work on right here in Baltimore City and in Baltimore County. I think they're fantastic. They tell a lot of story, and they're just really understudied. My friend and colleague in this department, Daniel Viette, is working quite hard to put together some work on those rocks, and I'm just super excited to watch that story evolve over time. But I think they're just really fascinating. They've got a really neat story to tell, and there's lots that we don't know, just a lot that we don't know. So look forward to some good information coming out about those rocks, I'd say in the next year or two.
Richard asked, does vegetation growing on mountains slow down erosion, or is that insignificant compared to tectonic action?
No, it certainly does. And I guess we're talking about, we have to worry about the time frame that we're talking about. But in those shorter time frames, they certainly do slow down erosion. But in the longer time frames, I suppose the tectonic processes are more important. And it actually just reminds me, I don't think I totally answered part of I think it was Steve's question about CO2. But we know that one of the really, really long-term buffers or controls of CO2 in the atmosphere is weathering. So weathering of mountain ranges tend to be overall a CO2 sequestering process. So over geologic time, it's been really important to help control CO2 concentrations. Sorry to muddle up two questions in one, but one popped into my brain as I was answering the other.
I put in the chat box, we had a recent episode, the last episode of MPT's Outdoor Maryland had a feature on us, and part of our fossil club was out in Western Maryland looking for trilobites. So I was just wanted to put that up there just in case y'all missed that.
Oh, I don't know who posted that, but I'm sure I'm not alone, but I adore trilobites. I love trilobites. I hunt them everywhere I can find them.
Or do you know any good places that we should be hunting them?
Well, Ohio and Western Pennsylvania. I mean, in Maryland, I don't know that many that are just truly awesome, but up around the Finger Lakes, there's a lot of options to get good trilobites.
All right. Any other questions for Jerry tonight?
Ooh, I hope not. I'm worn out.
Well, looking around, everybody is so smart now, and it gives us a different way to look and understand our world, and to look at the rocks around us. Every rock tells a story, and the rocks never forget. Who said that? I can't remember. Somebody wiser than I said the rocks never forget. So they're telling us all that we need to know. So I really appreciate your time, your knowledge, and sharing it with us this evening. I appreciate everybody for taking the time to come and learn with us as well. I hope to see you next week when we're going to some plants, looking at some plants, and woo, let's go out and yeah,
I think you will see me next week. I'm excited about next week.
Yeah, stay well, stay curious, stay outside, and go look at some rocks next week. This is that's your homework. Go and looking at rocks. Okay.
All right.
Take care, everybody.
Bye all.
Bye-bye, everybody.